Today, we want to talk a little bit more about rate of change. Yesterday, we talked about the rate of change of linear functions, including constant functions, quadratic functions, and exponential functions. We were identifying those functions by their rates of change, classifying those functions by their rates of change. That's a very mechanical thing for us to look at, which is appropriate. I mean, this is a math class after all. There's going to be some mechanics. But we want to think more generally about what we're doing. The three ideas that we're trying to connect are derivative, that's our new calculus idea, and we all feel fancy for it. Slope, which is an old idea that we have, and rate of change. So we want to take those three things and we want to connect them. Slope is telling us the rate of change of the function, the rate of change of y with respect to x. It's important to think about it in those terms. We want to think of the derivative as telling us the instantaneous rate of change at a point. This goes all the way back to the first day when we talked about, maybe the second day, the first day when we talked about approximating the tangent line with a secant line. We approximate the instantaneous rate of change by looking at an average rate of change and making the interval over the average rate of change shrink down to zero. We can't let it be zero because then we have 0 over 0. That's indeterminate. We got to figure out what 0 over 0 we are talking about. And that's when we have the derivative. And we learned our favorite shortcut for finding derivatives, because I think you should have that early rather than late. So that raises the question, what is it about slope that we care about? This means that there must be something about slope that we care about. When we start looking for applications of the derivative, which would be like, why are we looking at this derivative business? We care about applications of slope. All the applications of derivatives are the same as the applications of the slope. So if we were using the slope for something before, that's something that we can use the derivative for. That's why it's useful. This is tied to the idea of integration, because later on we're going to learn integration. Integration is multiplication, but one of our factors is continuously variable. So all the applications of multiplication are also going to be applications of integration, specifically the complicated multiplications where one of our factors becomes continuously variable. So we want to think about how we define the slope and what the slope means. And then we're going to look at an example today of our favorite calculus application of slope. So today we want to look at slope, and we want to think about how we analyze slope, and we're going to start by looking at the units of the slope. So recall that slope our slope, which we use the letter m, is the rise over the run. Those are just descriptive words telling us how y is changing divided by how much x is changing. Change in y divided by change in x. The triangle is a capital delta. So this is change in y divided by change in x. Change in y is just the difference in y values. Change in x is just the difference in x values. y2 minus y1 over x2 minus x1. We want to think about what the units of the slope would be. So when we want to write down the units of the slope, The reason that we want to write down the units of the slope is because if we can write down the units for something that we're measuring, then we can see what we're measuring. If we're not sure what this particular calculation is going to produce, we could write down the units of what's going on, and that will give us a clue as to what we are actually measuring. So the units of the slope are going to be the units of y. Then we're going to write the word per, and then we're going to write the units of x. This will tell us what the slope is measuring. We'll take the units of y, then we write the word per, then we write the units of x. We think of per as being the division symbol. Per is the division symbol. Not literally, but close enough. When we say the phrase per cent, we're meaning per 100. Per for divided by, cent per 100. Per cent means divided by 100. What's happening for every 100? When we write the slope, m, that's the change in y per 1 change in x, divided by 1. So per is the division symbol. We just take the units of the slope as units of y per units of x. I'm going to start with the one that we're going to work on today. It's the most common one. It's the one that was it's the example that we use in the book. Like I wrote the book. I guess if I'm going to use m, I'll just use s for some. So in this example, the units of y are meters. And the units of x are seconds. So the units of the slope in this case would be meters per second, which is a velocity or a speed. So the units are telling us what we're measuring. So we look at meters per second, and this says that we are measuring some kind of velocity or speed. Speed and velocity are related. Speed is just the absolute value of velocity. Velocity has direction, speed does not. Generally. Don't at me, physics people. Both will be measured in meters per second. Just whether we speed versus velocity just changes whether we care about which direction we're going. So when I was driving from home to work, I would say I was going 80. Sorry, this is being recorded. I was going 50 miles per hour on that section of 35. When I'm driving home, I will be going 50 miles per hour on that section of Highway 35 because that's what it says on my speedometer. I'm just measuring my speed. In terms of velocity, on my way here, my velocity was plus 50 miles per hour. But then when I'm driving home, my velocity would be negative 50 miles per hour because I'm going the other way. The related thing, so here, y is the height. There's two different things that we might care about that we might measure in meters. We might measure distance and we might measure displacement. So when I drive from home to work and then back again, I drive 5 miles from home to work and then another 5 miles from work back to home. I've driven a distance of 10 miles. My displacement at the end of those two trips is 0 because I'm back at home. So distance is just how far we went. Displacement is how far we are from where we started. So speed is more related to distance, and velocity we'll think of as being related to displacement. Is this a great explanation of physics? No, but we're not here for physics. We're here for math. And so we're just going to raid the physics book for applications of slope and rates of change. We're just going to say, ah, that's a nice rate of change you got there. And then I turn comments off so the physics people won't get mad at me on the video. Going to do the same thing in multiplication when we want to do integrations. I go, oh, that's some interesting multiplication that you have there, physics. Would be a shame if something happened to it. And all the physics instructors are like, oh, Leach, stop explaining physics to the students. You're very bad at it. I'm like, oh, I'm also very bad at explaining math, but no one stopped me from doing that. So the other thing that we care about is the thing that we've been talking about this whole time. If I have some change in y divided by change in x, I'm looking at an average rate of change. But we are interested in this class in looking at what's going on exactly at one moment. What is our rate of change, our instantaneous rate of change? We want to make a distinction between the average rate of change and the instantaneous rate of change. The average rate of change we represent with the slope of the secant. The instantaneous rate of change we're going to represent with the slope of the tangent. The slope of the tangent, of course, is the derivative. If this all sounds like stuff I've said before, that's only because this is all stuff that I've said before. If you're worried that I'm going to repeat this over and over again for the rest of your life in this class, I just want to make it sound more dire. Then that's only because I'm going to be repeating this like every day for the rest of your Calculus 1 life. Because we don't get songs stuck in our head by hearing them once or even twice. We get songs stuck in our head when we hear them over and over again on a radio to which we do not have access to change the channel. So I don't want to just make physics people mad. I want to make sure that everybody mad. So let's suppose that P of X is the profit in thousands of dollars for or of a production level of X units. So if we produce a bunch of units or sell a bunch of units, or even produce a bunch of, I don't know, it's a business thing. I don't know, do you take into account how many you're going to sell? Don't at me, business people. I'm only rating your subject for examples of marginal profits and costs. I have P of X, which is being measured in thousands of dollars, and I have X that's being measured in units, widgets, items that we're producing. If we look at the derivative, this will tell us the marginal profits. I don't know if that's a thing, doesn't matter. This will tell us the rate of change of our profits if we increase production. So the units of P prime of X there's that derivative. Derivative is slope. Units of derivative are going to be the same as the units of the slope. So the units of the derivative will be the units of P of X per the units of X. I should have called them something else other than units because it's just going to be units. But the units of P of X will be thousands of dollars per unit. As we take the units of P of X and we write per, and then we write the units of X. This will tell us how much our profit will change if we increase production by 1 unit. So this will describe the change in profit. It tells us the same thing that the slope tells us. How much y changes when x increases by 1. This will be the change in profit. We increase production by 1. One is a big jump, and instantaneous velocities or instantaneous rates of change are made at a jump of 0. So this would be the approximate, because once we change profit, our production level from whatever it is, x, to x plus anything, then our profits might change. So this is the approximate. Change in profit if we increase production by 1. Any questions? One thing to note here is that slope has direction on it. So we talked about velocity and having direction, driving from home to work, positive velocity, from work to home, negative velocity. Opposite, like emotional states. Driving to work is kind of more of a negative feeling. Driving from work to home is more of a positive feeling. Not for me. This is fun for me. One of my friends don't want to hang out with me on Friday. They go, hey, Leach, you want to hang out? I'm like, oh, yeah. Are you going to try to teach us math? I'm like, oh, of course. And they're like, oh, we canceled our plans. And then I see like on their Instagram, they're out having fun. But they're not really having fun, because how much math are they learning? 0. How fun could it be? Beside the point. So this is just a slope, and the slope could be positive or a slope could be negative. That tells us about what's going on with our profit. If P prime is positive, that means if we increase production by 1, our profit will go up. And being greedy capitalists, we're like, oh, yes, tell us more about the profits going up. Say it slower. And if we find P prime of X is negative, that means if we increase production, then our profit is going to be going down. So the slope tells us the direction of the function. If I have velocity as my, if I have the velocity while I'm driving and I tell you it's negative, so when the police pull me over, they say, do you know how fast you were going? I'll be like, oh, negative 50 miles per hour. You're like, oh, why is it negative? Because I'm going home, dumbass. Don't ever say that to the police. In fact, just don't talk to the police. That's just like rule number 1. Don't talk. But anyway. Also, don't be like, oh, it was negative 80. It's like, oh, the speed limit is 50 here. Michael, and negative 80 is less than 50. Dumbass. Don't ever throw that on. Any questions? Comments? Deep thoughts? I'm gonna get pulled over now. I'm just kidding. The police aren't watching. All right. So this is the thing that we're trying to measure. The idea that we want to get across, this derivative thing, this new derivative thing that we have. We have a way of finding it. We have that shortcut for finding it. We know where it comes from. It comes from trying to find the slope of the tangent line. And we're saying that slope of the tangent line is going to be our instantaneous rate of change. Rate of change is a general term for a lot of things. Every application that we had for the slope before is an application for a derivative. We just make it on a continuously variable function. That's the new thing that calculus brings. We take all the stuff we did before and make it continuously variable. What's worse is that I made my reference to getting a song stuck in your head. And now I have a song that easily gets stuck in your head, stuck in my head. I'm like, oh, a song, like a song that gets stuck in your head. And then my brain's like, well, I know one of those. And I'm like, oh, you motherfucker. I was trying not to have that song in my head. It's like, oh, it's there now, so enjoy. Great. The interesting thing about deep classrooms like this, I kind of go far back, is I know the limits of my eyes processing, looking at a group of people and seeing how many there are. It is 6. When there are 6 people in a row, I'm like, oh, 6. Grab 6 and hand it out. When there's 7, I'm like, oh, and it like takes a whole minute to figure it out.